Hi, so thank you for attending. My name is Liam. I'm one of the technical sales managers at I Holland. So hopefully you all know about I Holland and who we are, but just in case you don't, just a little bit about us. We were established in 1946, so a very long time ago, and we are actually the longest established tooling manufacturer in the world. All that we do is produce tablet compression tooling. We also supply equipment that supports and maintains that equipment, and that is actually where I started in the business. So I have been with I Holland for 9 years. I started as a service engineer, and then for the last 4 years I've looked after markets from a commercial and technical perspective, and I've actually looked after Turkey for all of those years, so this is one of my favourite places to visit and come, so it's very nice to be here. We are a single manufacturing site in the UK, so if anyone has ever been to the UK, we are in Nottingham, which is right in the middle of the UK, with excellent transport links, which means that we can get our tooling to you as quickly as possible. You are all welcome to visit I Holland, and if you are ever in the area, please come and see us and have a tour of our factory. It is quite impressive, especially how much machinery we can fit in a very small space. I come to all of your sites, which have lots of room, and I think, wow, I would love this room. We have to cram as much into a very small space as possible. We export to around 90 countries a year, so we truly are a global operation. And interesting enough, get to see some very exciting things. Hopefully you are all familiar with tablet compression tooling. However, if not, just to point out, we have the upper punch on there, and just a few key dimensions, one I would pay particular attention to. We have the overall length, very important in a minute, and the working length. These are what we would class as critical dimensions. What we will show you during the demonstration session is the tool management system and how that can actually monitor and record those for you as well. The die and the lower punch, and of course more recent technology, the segment. So we need we certainly need an upper and a lower, and we need either a die or a segment to produce a tablet. This is what we make. I'm going to change things up. So I've tried to think local on this one. So the bridge we have over here, the Bosphorus Bridge, how many punches, if we laid them end to end, so head to tip, would it take to actually cross the Bosphorus Bridge? This number is a lot bigger than you would think as well. And just a little clue, it is the total length of the bridge, not the span. Okay. So that might help. So I'll give it a few seconds for you to scan the QR code on screen and have a go at answering that one. I was surprised when I had to calculate this, how many there were, to be honest. It's quite a big number. Okay. So into what we're going to talk about today, and it's really how to choose the correct specification. So we're going to look at this from two aspects, material and steel, and then also coating applications as well, and how they can affect what we need to choose for our tablet compression tooling. So when we choose a steel, what are we looking for? It's a combination of many factors. So we're looking for strength, how much force can we put through it? The tools are rotating in our tablet presses sometimes extremely quickly. You can barely see them. So that is a lot of cyclic loading, a lot of fatigue loading in there, so we need to ensure that the steel can withstand that. Toughness, again, we don't want any breakages. You don't want any bits of metal flying around in the tablet press. That's really bad. And abrasive wear. Some formulations are more abrasive than others. But if we imagine when we're compressing tooling, or when we're compressing tablets, you've got that formulation and it's sliding against the face of the tool. If we have an abrasive formula, we can sometimes see that reflected on the punch tip face. It can look very scratched. So we need a material that can withstand that as well. That actually comes in two factors. So we have the abrasive part and that friction element, but we also have the hardness, so the impregnation of very hard granule, and that can be reflected in something we call pitting, which is like pinpricks on the face of the tool. And of course, as we look more and more at containment, wash-in-place presses, corrosion resistance is becoming more relevant as well. So when we're looking for tooling steel, you're often looking for materials that have higher benefits in toughness and strength rather than corrosion resistance, because unfortunately corrosion resistance tends to reduce those. So again, we're always looking for a balance. Now, there are many different types of grades of steel available, and they can be called many different things. So it's just important to bear in mind, different grades of steel can be called different things based on the standards that they are measured to. What I would say is really important is actually the refinement of that steel. If we talked about traditional steel, that is an image there under very high magnification, and what you can see in white is the non-metallic inclusions. We would call this dirty steel because there is a lot of them in there. What you will also see is they are in quite distinct lines and boundaries. What that actually impacts and reflects on is when you're compressing tooling or when you're compressing your tablets, we have that abrasive element of the product sliding against that. When it wears the tooling down to one of those layers, you will actually get a large piece of material fall away because it separates the whole layer. So that's what we want to try and avoid happening. Okay? That accelerates wear. That's not good for our production process or our output. So it's always better to try and refine your steel, as we have done there. So it goes through a process called electroslag remelting. So we heat it up. Those non-metallic inclusions, or at least most of them, come to the surface and we take them away. That is then refined back into that steel. It's also referred to as ESR steel. So ESR stands for electroslag remelting, and that is really critical to have that as a tooling steel. So all of our steel that we use is ESR grade, precisely because of this reason. You can take it a step further, and this would only really be useful if you have a very, very abrasive product, into what we call PM. Now, PM stands for powder metallurgy. So we take our refined steel, grind it into a powder, and then reform it into a very uniform structure in here. So again, this makes it really, really abrasion resistant. Unfortunately, that does come with quite a high cost as well. So there are other ways that we can achieve abrasion resistance, which we'll talk about with the coatings. But if you have a very, very abrasive formula, vitamins in particular, this might be something to consider. I mentioned on the last slide about different grades of steel. This is actually where we separate ourselves from other suppliers. So we do not use any commercially available steel. We use enough steel to actually go to the manufacturer, the foundry, and say, this is our recipe, make us our recipe, and this is our steel that we do. So our steel is called pharma grade. And they, again, all have different properties, which we'll see on the next slide, as to which one is the right one to choose. So again, if we're talking fracture, how much force we can apply, then HPGS is the steel that gives us the most force through there. At the opposite end of the scale is tungsten carbide. So tungsten carbide has very, very low resistance to fracture. Yeah? It doesn't make a suitable material for punch tips. Wear resistance and dies, fantastic material, but not really suitable for punch tips. That is where we would look at something like a premium, which has a nice balance of resistance to fracture and wear resistance. So it's always a bit of an art. We're looking for, what do you want? Do you need a high force, or do you need a longer life? And again, this is where the coatings will come into later. We can balance our steels with our coatings and try and maximize the benefits. And that's really why we heavily promote coatings, because with steels, you're always sacrificing one of the aspects. With coatings, we can balance them. Corrosion resistance. Yeah. Hopefully relatively straightforward. Stainless steel is where we need to go. So stainless steel will give us our most corrosion resistance, significantly higher than standard and quite a bit higher than premium. Again, if you're using a wash-in-place press, this is where we will tend to look. We just have to be careful because the press force is not as high with stainless. So we just need to be careful on that one. So into our coating range. Why would we apply a coating to a tool? It's one of three aspects or reasons. They can offer excellent anti-stick properties, wear-resistant properties, which we'll talk about, and again, corrosion-resistant properties as well. So, not all coatings are anti-stick coatings. However, all coatings have elements of anti-abrasion and corrosion resistance as well, which we'll see in a second. How do we coat a tool? This is the traditional process of coating, so it's an electrolysis process where the tool is placed into a bath of water, and then we have our target material, chromium, and then via the process of electrolysis, we attract to the tool that chrome content. When it forms in plates like this. So although the tool will look very nice and shiny, normal, when you look under very high magnification, you can actually see these plates here. That's a byproduct of this process. The other thing we have to consider is we actually introduce hydrogen from the process into the steel. That hydrogen process actually that hydrogen in the steel weakens the steel. So whenever we apply hard chrome, which is what we can actually see here, hard chrome will weaken the tool by 20%. So if you've ever seen our tablet drawings, in the bottom right corner, we have a chart. You'll see an example in a second. And it will show you two columns, one for hard chrome and one without. The hard chrome is 20% less press force than that one. So it's a traditional coating. It's still very relevant. I would say probably about 35 to 40% of the tooling that I Holland supplies that's coated is hard chrome. But we are very quickly moving away to that because we have more advanced technologies now. Most modern coatings are applied via a process of PVD, or physical vapor deposition coating. These are done in a vacuum chamber, so we have no hydrogen to introduce to the steel. That's the first big benefit. So PVD coatings do not weaken our steel. We retain the same properties and the same press force. We also get a much more consistent and even result, and that is actually based on rather a unique process. There are two types of PVD coatings. One is arc. That's the most common type. Or, sorry, just go back a second. This process here called E-beam. So E-beam is a more controlled energy beam of process where we have our target material, in most cases chrome. We energize that, and again, we are attracted to the tooling, which gives us a much better surface, much more even, much more consistent, and that provides a couple of benefits we'll see in a second. Don't know why it was a bit odd. So, coatings. There's a lot of them. Yeah. Why is there a lot of them? because quite frankly, they all have slightly different properties and all have slightly different reasons for applying them. There are a couple of things on there that actually aren't coatings, but are very relevant. So the first one is SAR, which we will talk about in a second. XDF head. So Ahmed mentioned a lot about dwell time and how that can play a massive influence on tableting. What we have down there is actually an elliptical head. So that head can be applied to standard B or D punches and can be run in tablet presses without any modification to that tablet press. The only thing that we have to consider is if you're running a round product, then we'll need to key the lower to prevent it actually turning, and the upper as well. So we don't want that turning in the cam track, but it gives you over 50% more dwell time compared to a standard punch. I actually really like this because it's very easy for you to test if this is going to be relevant and if this is going to work for you. If you have a problem such as capping or sticking, one of the things that you can try is to slow the press down. And when I say slow the press significantly, 30, 40% slower. And if we see positive results, the XDF head will allow you to run at that original speed whilst maintaining that same level of dwell. So we can maintain the output, but have that dwell that we need to form that tablet. And again, something you can try very easily for free. The other one that's also important is SAR 2. So again, I'll mention SAR in a minute and how it works, but we're taking it the step further to actually predict how dwell will play that influence and role. So that will be coming out in the coming year, so keep an eye on that one. So I mentioned there were lots of coatings. How do we go about choosing the right one? And again, it's what we're looking for from that coating. So if we're looking to increase the life, then it's a very easy selection. We look at the hardness of the coating. Steel hardness is measured in Rockwell C. Coatings have a different scale. It's a different test that they run through. And that's the Vickers scale. So HV on there. If we were to convert Rockwell C to Vickers, we'd be talking between 600 and 700 Vickers. So what we can see is hard chrome, HC, down the end, is 900 Vickers. So hard chrome is already harder than uncoated steel. So if we had a hard chrome coated punch and it was run alongside an uncoated punch, the hard chrome punch would last slightly longer. But again, when we go to CN, chromium nitride coating, that takes a big leap forward. That actually goes to 2,000 Vickers. And actually our hardest coating, RS, resilient surface, that's 3,000 Vickers. And there's a case study at the end of this we'll show, which actually shows the impact of just what that coating can do. Corrosion resistance, again, this is quite easy to select. The coatings are all tested, in fact our steels are also tested under extreme pressure or under extreme environments. We actually salt spray test our steel. So it's put in a chamber and salt water is sprayed at it, and we go back and check it every 2 hours. All of our steels, including stainless steel, show corrosion after 2 hours. Now this is very aggressive testing, so it's not going to impact what you see in reality, but it gives you an idea of just the difference, again, coatings can make. So hard chrome, 2 hours. After 2 hours, we already see corrosion, and that gets back to that plate form that you see on the surface. Because you have the plates, you have the boundaries in between them, and that's where the corrosion starts to form. The PVD coatings, because they're much more even, they're much more consistent, they have better structure, we do not see that corrosion form straight away. The coatings that actually demonstrate the best corrosion resistance, as you would perhaps expect, are our thicker applications of those coatings. So CN and CX chemically are the same coating, have the same hardness, but CX is a thicker version. So it takes longer for that corrosion to take effect. They also last longer as well. Now the actual tricky part, when we get to sticking. How do we choose the right coating for sticking? And we go back to that list with many coatings. Why are they there? Because they all present slightly different anti-stick properties. Traditionally, and to an extent still valid now, it would be based on trials and formulations, and we would run your product with many different products and see which one gave the best results. That can be costly, it can be time consuming, and we know in the reality in the modern world is we need to potentially get out and get our product to market quickly. What we looked at over a few years was actually what formed sticking and how could we do that, and that was based on a partnership that we did with our local university, the University of Nottingham, where we looked at all the causes of sticking. We actually ran many experiments. One that was very important is this one. So this is AFM, which is atomic force microscopy, and I really do not like saying that word, so I keep it to AFM. What you will struggle to see here is because this chamber is actually about this big. It's very, very small, but there is a very small needle in there, and onto that needle we can place any formulation, and that needle can then be pressed into a surface. So we can change the surface, we can put all of our coatings in there, all of our steels in there, and we press the product into that surface, and then we pull it away, and we can measure the force taken to actually separate it. Now that's a very small force, it's measured in nanonewtons, so really, really small, and we can repeat that many times. Now again, it's quite a time-consuming process. We ran 2 years of experiments to the point where we really upset the students because we were taking all of their time. So we had to switch to running them at night. Again, to run that, again, very time-consuming. So what we did was we built a mathematical model that replicates that experiment, and that is SAR. So this was a £500,000 project in the end, significant investment in this one. To date, SAR has done nearly 3,000 predictions. So chances are if you have a sticky formulation, we have run a SAR on it, or in cases multiple, and we can then give a result of particle adhesion based on that. Now I must caveat and say sticking can also be caused by other forms, profile, environment, but one of the leading causes is just material attraction, and we can measure that with SAR. So very quickly, very simply, it takes us a few minutes to run that prediction model as opposed to the weeks that you would have to run those trials on. Now I do feel like I'm attacking hard chrome here, and to be honest I am. It's a very old coating now, and to be honest, it needs to be replaced because of its weaknesses are significant. It's very, very old technology. It cannot be improved on any further. It's reached its peak of technology, so we cannot get any more hardness from that level, and we cannot get any better on that process. One of its biggest issues, and the reason that it will probably be banned eventually, is actually the waste product of hard chrome is very, very dangerous. It has to be specially destroyed. Hard chrome itself is perfectly safe and perfectly fine. It is the waste product on that one. But my biggest issue with it is this. It's the press force. So the reduction that we get between hard chrome and no hard chrome is massive. So no hard chrome PVD coatings would all fall under this category. Unfortunately, hard chrome falls under this one. Again, just to show that difference, those plates, and then some of the PVD coatings, the surface is far more even, far more consistent, and that will give you longer life as well. After that. So some real-world examples. I appreciate you're never going to read that. These are available on our website to download. This is a case study we did with Novartis, where they had a sticky product. And again, using SAR, we were able to provide the right recommendation for them so that they could choose the best coating for that. What is actually my favourite case study? If I've ever been in a meeting with any of you, I potentially might have shown this one because it is my favourite one. This was done with a customer in the UK. Actually used to be my customer. I looked after them for a long while. Thompson and Kappa. They do a lot of contract manufacturing. And one of their products was extremely abrasive. That was uncoated steel after 4.5 million tablets. Again, I appreciate you can't really see, but the edge on that punch is non-existent. It has been worn away, and the face is very, very pitted and very, very scratched and abraded. So 4.5 million tablets. We applied RS coating, our hardest material, our hardest coating, 3,000 Vickers. That's the punch after 35 million tablets. Still looks brand new, and in fact, could keep going for a long, long time. Now, RS is not a cheap coating. I do have to stress that. The tooling cost on this project went up by 78%. So that's a significant increase in cost of tooling. However, the life of this tooling was vastly more than that cost increase. So it more than paid for itself. What I would say is if you do have any questions, particularly about the coatings, obviously please feel free to come and see me. I will be over there demonstrating the tool management system as well, which looks after the tooling from its arrival through its production process, through any problems that we might have, and then through to destruction as well. But again, if you do have any questions, please come and see me. And thank you very much. Hopefully you could get the right question or the right answer to the bridge.